Oh, welcome. This is our second lecture, lecture number 2 on radioactive emissions. Let me just jump into this. When an unstable nucleus decays, remember last time we gave the recipe for an unstable nucleus. Simplified, it's a nucleus that does not have the correct ratio of protons to neutrons, or neutrons to protons, as we put it last time. So such a nucleus will decay, and we have to say what it means practically for a nucleus to decay. When it decays, there are two products. Well, one thing that was quickly apparent to the early researchers was that these nuclei decay into new elements. Specifically, when one nucleus decays, it's the nucleus, or I should say, it's a new element's nucleus. Or let's put it a new nucleus. A little vague, but that's okay. So we're going to start with an old nucleus and get a new nucleus. And in the process of doing this, we have to say something else. This nucleus is going to be more stable than the previous one. Again, stability is relative. You can have something that's radioactive. By definition, that means unstable, but it's going to be more stable than the nucleus it came from through decay. And of course, as was initially apparent, we have some sort of radiation that is emitted. Radiation, or as we said here, radiation means a radioactive emission. We really talk about 4 of them in this class. One, of course, is the famous alpha particle. One is something called a beta particle. There's a gamma ray. And as was discovered, some decades after these were, there's something called a positron. Notice these are Greek letters. You don't have to memorize these. These are all listed on table O for you, which we're going to unpack in a few minutes. Now, isotopes that have an unstable nucleus have a special name. Such isotopes are called radioisotopes. In other words, they're isotopes that are radioactive. They undergo decay. They break up into new elements, new nuclei that are more stable than what they came from, and of course they pump out radiation in different forms. Now, it turns out all elements have unstable forms. So in other words, all elements have what we call radioisotopes. The one that you've probably heard of before coming into this class would be something like carbon-14. Now, carbon makes all biological organisms possible. They're the backbone. But of course, there are some forms of carbon that are totally unstable. So they can come from, in other words, elements number 1 to 83 have perfectly stable forms, but then they have unstable forms as well. As we said in the previous lesson, if you're element 84 and above, these ones only have unstable forms. 84 and above have only unstable forms. That's good. You're always going to get a question on that in the test, either part 2 or multiple choice. So just commit that to memory. Stable forms. Now, you are given a lot of help in this unit in the forms of Table N and Table O. Today we're just going to be looking at Table O. We're going to unpack. You're going to see that just answers a lot of questions. Merely referring to it, you'll know things like the mass, the charge, and of course the symbols are given to you as well. Let's take a close look at these. So first of all, according to Table O, an alpha particle is symbolized as an Greek A, the alpha. A Greek beta particle is the letter beta in Greek with a little negative sign. There's something called a positron, which is also given the Greek symbol, but this has a positive charge. A gamma ray is Greek gamma. Now, it makes no secret about, it gives all of the information that you need. It says that alphas are 4-2 or they're 4-2 with an He, meaning that an alpha particle is the same thing as a helium nucleus. Now, what's nice about this is that there's no mystery. It has a mass of 4 and a charge of positive 2. The beta particle is it's written on table O as having a mass of 0 and a charge of negative 1. It's either written notated that way or notated this way. So, very simply, a mass of 0. Remember, when we say a mass of 0, it means practically 0, relatively 0. There is some mass there and a charge of negative 1. For this reason, a beta particle is the same exact thing as an electron. Now, don't be confused. Remember, when a nucleus breaks down, these particles are released. I don't want you to think that that means that electrons being released from the nucleus in the process of decay are in the nucleus. There are no electrons in the nucleus. These beta particles, these electrons, are newly created when something happens, as we're going to see, to neutrons. Positrons, be careful, are the same as beta particles, except they have a positive charge. They're positively charged electrons. They're also called anti-electrons. They're what we call antimatter. Anti-electrons, when they meet electrons, will destroy the electrons and themselves be destroyed in an explosion, in a burst of energy. It's very interesting. Positrons, mass of 0, charge of positive 1. Now, gamma rays are notated with this Greek gamma, a top number of 0 and a bottom number. Now, when we say that these have a mass of 0, we mean true 0. Gamma rays are pure energy. They don't appear as mass, they appear as energy. They're chargeless, they're uncharged, they're neutral, just like neutrons are. So if we were to take a moment and say, if I were to accelerate these particles, if I were to accelerate an alpha particle, a beta particle, a positron, and a gamma ray, and I sent them between a electrical field, one side positive, one side negative, we should expect to see the following. That positively charged alpha should follow the C path. Why? Because they're attracted to the negatively charged side and repelled by the positively charged side. The betas, on the other hand, will follow the A path, the A trajectory, because positive attracts negative, and negative is repelled by negative. The positrons, again, there'd have to be a vacuum in here. Because remember, if this were to encounter an electron, it would just be destroyed. It would never continue its path. It would never complete its path. And so this is going to follow the same trajectory as the alpha beta particle. Just as a neutron would, being neutral, the neutrally charged gamma is going to be unaffected by the field. So it will not be attracted or repelled by a positive or negative. So it just sticks to the middle path if accelerated. All right? So then, just to complete here, electric field, the alphas move towards C. The betas move towards A. The positrons move towards C, which is a negatively charged pole. And the gammas are unaffected, so they just lie down the middle. As far as the energies go, it really has to do with what we would call the momentum of particles, the kinetic energy. So at a certain amount of energy, if you have a large mass, you tend to lumber along really slowly. So we say that you have a rather low kinetic energy. As the particles get less massive, their energy increases because their velocity increases as their mass becomes insignificant. We would consider both beta and positrons medium in their energy, and the gammas are of extremely high energy. And we relate this amount of energy to how far these particles travel in air. So I'm just going to mention a couple of things here. I want to indicate, relatively speaking, how far these particles will travel in air before they stop. Well, if you're an alpha particle, you're not going to get very far, only a few centimeters in the air. That's all you get. You just essentially bump into enough air particles that you're stopped dead in your tracks. Now, if you're the smaller, faster beta particle, you're going to get actually, let me use green here, a meter. You're going to get about a meter in distance in the air. We're not going to talk about positron. Remember, a positron bumps into an electron, it's toast, so we can't say how far it'll travel in air. It's going to get annihilated. Gamma, well, it's so small, it's really sizeless, and it's just energy, it's fast, so maybe it's going to get a kilometer or more in air. Again, that's related to the relative amounts of energy that you have. Now, related to that, what will stop them? Well, let's say that you're in range of an alpha particle. You're not in too much danger, provided you hold up a piece of paper. Paper is not very dense, but it's dense enough to stop an alpha particle. If you're a beta, maybe about 0.5 centimeters of aluminum. Aluminum isn't that dense of a metal, but you don't really need much of it to stop a beta particle. Now, if you want to stop gamma, you need a really, really dense material like lead. And not just lead, you're going to need about 10 centimeters of lead. That's about 4 inches of lead. That's about 4 inches right there. That's a pretty thick piece of lead in order to protect you from these gammas. They penetrate, and then they're stopped eventually. But they're extremely penetrant particles. Well, that is the second lesson. Again, the whole point of this was to give you an appreciation of the quantities associated with these 4 radioactive emissions and some of their, an appreciation of their relative ability to penetrate material. We'll see you in lesson number 3.